Okay, guys, we'll finish just one topic of chapter 2, and then we'll go for chapter 3. Chapter 3 is nuclear chemistry, which is really very, very short chapter, but we will do a lot of problem sets, so you can then share with me your knowledge about nuclear chemistry if you have some knowledge on this. So, chapter 2, we stopped on the last topic, which is the atomic radius. If you can recall, atomic radius, and we said atomic radius is the distance between two nuclei of the same atoms. So if I have here an atom, correct? This is the nucleus here. So then the other one will be here somewhere. So the distance here, this distance here between two adjacent nuclei, this is the same, by the way, sorry about this. This is the same, two atoms of the same kind. There, when they come to adjacent, they come very close to each other. So the two distances between the two adjacent nuclei is called atomic radius. So we'll say this is AR. Then in the periodic table, as you will see, the AR, the atomic radius of an atom, will increase from the top to the bottom of the periodic table. So let me take this one out, and let's look at the let's take this one out and look at the periodic table trend. And then we'll put the whole image together here. So if I look here at the atomic radius, for example, if I look at the atomic of the element group number 1, metals, not hydrogen is the top, but hydrogen is not metal. So lithium, sodium, potassium, and goes all the way to francium, group number 7. So this is period number 2, the periodic table, period 2. This is 3. This is 4, and it goes on to 7. 7 is the last one. So it looks like the atomic radius AR is from the top here to the bottom, to francium here, going down. It really increases. So francium has the largest atomic radius among of group A. Group A, the metal. We are not considering the hydrogen. Hydrogen is totally different. It's non-metal. It's non-metal. And in any way, it has a very, very tiny atomic radius compared with lithium and sodium and potassium and francium. So the atomic radius, this is called, when you go from the top to the bottom here, this is called group. It's called what? Group. So within the group, from top to the bottom, the atomic radius increases. Now, if we go and look at the other side, the period from left to right, so this is top to the bottom, we call it group. So the atomic radius increases within the group from top to the bottom. Now let's look at atomic radius when it comes from within the period from left to right. Let's look at this and see how does it look like. So we'll be looking so if we are looking at the group here within, the atomic radius within the period, within a period of periodic table, then what you will see here, when you see this, you will see that's from left to right, the atomic radius AR will decrease. So see the opposite. Within the group from top to the bottom, increase, from left to right will decrease atomic radius. So if you look at the group number 2, lithium, and go all the way to the end of the group here, to the noble gas, so you will see that that's the atomic radius will decrease. So if you go to the, I think it's helium, so this you'll see all the way, this is not helium, I think is helium, neon, I think, yeah, neon. So the last one here is the AR will decrease. So from left to the right of the periodic table, the atomic radius will decrease. So the trend is atomic radius, the distance between two adjacent nuclei of the same atom, will increase within the group. The group is top to the bottom, will increase from top to the bottom, and it will decrease from left to right within the period. The period is the arrangement of the elements from left to right, so it will decrease. So that's the first trend of the within the periodic table, of the elements within the periodic table. So let's look at the other one. We have to look at the ionization energy. What we mean by ionization energy? It turns out to be ionization energy means you are making some ionization to the element itself. So you will see those metals, they tend to have higher ionization energy. So ionization energy, so we'll say I, that's abbreviation, ionization energy here. We'll say I, E, abbreviation, atomic radius AR, ionization energy is IE. So it looks like within the group, as I said, of the periodic table from top to bottom, it behaves opposite of what? Of the atomic radius. Atomic radius increases. This one here, the ionization energy will decreases, correct? Within then the period here, within the period of periodic table, the period, which is from left to right, opposite to the periodic table, decrease atomic radius, but this one here will increases. So the ionization energy will increase. What we mean by ionization energy? Ionization energy is the amount of energy needed to pull out electrons out of valence electrons or electrons. Valence electrons, those electrons are found in the last orbital, as we say. The last orbital hosting those electrons are called valence electrons. So if I have, for example, magnesium, group number 2A or 2, magnesium, an element, is a metal. As you can see, ionization energy is always larger in metals because metals, they tend to give away their valence electrons. The non-metal, on the other hand, they like to have, they don't give away their electrons, they like to take in electrons from adjacent atom surrounding them. So magnesium can be ionized if you put enough IE here, and you'll see magnesium is going to be 2 plus 2 electrons. Okay, guys? So it has 2, of course. So magnesium goes to first one. So if I look at this, maybe I will take here, this one here. Let me take this one here. They don't explain this. So magnesium it has 2 valence electrons, so it will have 2 magnesium here. So it will have 2 ionization energies. So Mg, first it loses IE, 1, ionization energy 1 will be Mg, always 1 at a time, plus it loses first 1 electron. So then the Mg plus goes further, IE2, Mg 2 plus 1 electron. So you can see that those are 2 ionization energy here, because magnesium in the group number 2 and the valence electrons are 2. So therefore we need 2 ionization energies to accommodate the ionization of magnesium as an element, metal, of course. So now the question is, which one, when we compare those 2 ionization energies here, this versus 1 versus 2, it turns out to be that this magnesium loses 1 electron. This electron is still holding to magnesium, because this is very close, the first one, very close than the other one. So therefore you need to put a lot of energies to get this electron all the way out from the nucleus. This is very close. This is very close to the nucleus. Okay, so you will see that all the time the first ionization energy is larger than the first one, larger than the second. If we have a 3 ionization energy or 4 steps ionization energy, so the last one, the IE4, will be the smallest one. This one will be larger because the first electron is very close to the nucleus, so it will not be given away easily. So always the first ionization energy is higher in amount. So that's the amount you have to put in to get these valence electrons out. Okay, guys, this is ionization energy, and the ionization energy, repeating, it increases within the period from left to right, opposite to atomic radius, and it decreases within the group from top to bottom. Atomic radius is totally opposite. Okay, so the third trend is is electron affinity. Almost electron affinity is the opposite of ionization energy. Now we have the metals are giving away their electrons. Now you will see the non-metals are taking in those electrons, okay? So let's look at this. So we have electron affinity. Okay. So this is, take this one out. Okay, guys. The third one, electron affinity, is EA, and this is really amount of energy needed to pull out electrons towards an atom. So if you look at this, for example, chlorine will have an atom neutral, like to have one electrons to be one negative, so it will be chlorine negative. And this way here, it needs EA. It needs EA, that's electron affinity, it needs an energy to help electron neutral element to pull out this electron from the neighborhood or from the vicinity around it towards itself. Then you will get this negative charged atom will be this called chloride ion. This is an ion that's chloride ion. So this is the affinity here, electron affinity. Now, if you have metals such as phosphorus, you'll have three of those. You'll have three. So phosphorus, for example, that's an element, and at first step you get EA1, phosphorus, one negative, correct? And then the one negative here, take another one, get phosphorus, two negative, and then the two negative takes another one, and the last one is P3 negative. So those are electron affinity 1, electron affinity 2. This is EA2, and this is EA3. Those are electron affinities, and this amount of energy needed for the atom or for the element to pull out those electrons. And this is unique for the nonmetals. Ionization energy is unique for the metals, while electron affinity is very unique for nonmetals. So we have three. We have atomic radius, we have ionization energy, we have electron affinity. Now the behavior of this is the same like ionization energy. So within the group, so the electron affinity from top to bottom decreases. Same like the ionization energy, the opposite of atomic radius. Now, from period here, from left to right, it will increases. So that's quite similar to the ionization energy. The only thing is ionization energy and electron affinity will behave in the periodic table for the elements the same. However, the atomic radius is quite the opposite. So that will conclude chapter chapter 2, which you'll have then until I think the 15th of February. So you have 1 week to finish it. Any question before we go to chapter 3? Chapter 3 will not take that much of time, but if you look at this, we'll go for chapter 3 if you don't have any question. Any question, guys? Any question? Any question? If you can't talk to me, then you can write the message here in the chat box at the bottom. If you have any question, if you can't talk to me, I think you can't talk to me. No problem. Because everybody says that he or she can hear me. So if you can hear me, then you can talk back to me. Any question, guys? Any question? Hello? Any question?
No, Professor. Everything is understandable.
Okay, good. Thank you. Thank you. Good. So those are the 3 ones. And let me just wipe all this out and then go for chapter 3. Chapter 3, the easiest chapter ever. And you'll never believe it. We might be finishing the whole thing on time. And then when we come back Tuesday, we'll do some extra more worksheets. That's what's help. Okay. So I just escape out of this first. Okay. It's not going nowhere. Trying to minimize it, go back to the I stopped sharing so I can go back, minimize. Okay, let's see. Share. Okay, went back to sharing now. Okay, guys, chapter 3. Chapter 3 is about nuclear chemistry. So we'll go for chapter 3. Okay, chapter 3 here. Chapter 3, guys. Well, chapter 3 turns out to be about nuclear chemistry. Well, before we go to nuclear chemistry, we have to recognize something called isotopes. So what is really an isotope? Well, an isotope, maybe we talked about this before, maybe not, but an isotope or isotopes for the same element, those are different modifications found really in nature with different abundance. They're found in nature because for the same element, because the number of neutrons in each of those modifications differs, correct? It's different. So isotopes are different different modifications found in nature for let me just say here, and then maybe come here for the same element due to different number of neutrons. So this is just a definition, and we'll look at some of the isotopes. Very famous isotopes are isotopes of carbon. So let's look at the isotopes of carbon and see how they look like. Isotopes of carbon, there are 3 isotopes of carbon found in nature. We might have to cover this one here, but it's very good because that's the way we can learn about the about nuclear chemistry. Before we start nuclear chemistry, we have to know what those isotopes. So if we look at this, we have, and I remember that we covered this, but we have carbon here. Carbon, let me just write it again here. Carbon here has the atomic number 6. Atomic mass is say 12. It's not really 12. It's with the abundance here there. So this is the carbon found in nature, but I think it's 0.0112, 01, I think, or something like this. So you can look it up. So carbon has 3. This is the carbon. That's the general carbon found in your periodic table. However, in the reality, carbon has 3 modifications. So those 3 ones, let's put them here. And let's put here here is number of protons, number of electrons, number of neutrons. So we have, take this one here out. We have carbon 12, carbon 13, carbon 14, correct? So if you look at this, and I think we mentioned that, I think I remember in the class, but at least it's very good to know how we do this. So carbon 12, how many does it have the protons? Well, the protons is the atomic number, correct? So 6. Since neutral not charged, the electron is 6. So all those here, regardless, 6 protons, 6 electrons, 6 protons, 6 electrons. Those are. Now the neutrons is totally different because the neutron is, we have to round this one here to whole number is 12. So neutrons here will be 12 minus 6 equals 6. 12 is the atomic mass, minus 6, minus the protons, because atomic mass is the sum of protons plus neutrons. So here's 13, atomic mass, minus number of the protons, always we subtract number of the protons, equal what? 7. So this is 6, this is now 7. So here's 14. 14 minus 6, that's your 6 here, is 8. As you can see, the number of protons and electrons not changing in all those 3 isotopes, correct? The only thing changing in those isotopes is number of neutrons, and that's what we call them. That's what we call them. Isotopes, because they are differing for the same element. They are differing in number of number of neutrons. So I think we covered this one here before, but at least it's very good to know about those isotopes. Now, if we can, they come with the abundance itself, so they can come with their abundance, and as you can see here, the abundance in nature for this carbon-12 is about 99%, and this is about 1%. So this is very close to 0%. Is 0.0000 something percent, so we care about 0%. So this is the natural abundance of found. So the carbon-12 here, that's what is found because 99%. So we can see that's the most abundant one with 99% almost. So this carbon here, 12, called charcoal or brown coal. That's very safe. It's not does not radiation. It's not really do any radiation, correct? So we can use that at home. But carbon-13, carbon-14, they are very dangerous because they can give off some radiations. And that's what lead us to what? To nuclear chemistry. So up to the element 19, which is potassium, everything is good. So we don't expect that much of radiation. Then we'll go up to atomic number greater than 19. Calcium is 20. So then the radiation will come off. When you have those radiation, then you speak about nuclear chemistry. Those radiation coming not from the valence electrons spinning around the nucleus. No, they are coming because there is a lot of stuff going on in the nucleus, causing it to be unsettled and give off those type of radiation. What type of radiation we have? Well, we do have several radiations coming out the nucleus, and we can go through this radiation together. As I said, this is a very simple, what they call it, a very simple chapter. It's not very, very difficult. We'll do some when we come back. A very short chapter too. So now, what those radiations are? It turns out to be, we have alpha radiation. Alpha radiation is nothing less than just helium atom with atomic mass, with atomic number 2, atomic mass is 4. Remember, atomic mass is greater than atomic number. Atomic number is just number of the protons, which is equal to the number of electrons. However, the atomic mass is the sum of the protons and neutrons, so it's bigger. So alpha radiation is helium, correct? Now, you have beta radiation. Beta radiation, radiation here, is coming from the nucleus, not from outside. Those are electrons. Those are electrons, but not from the valence electrons or from the core electrons. No, those are coming from the nucleus itself because of the collision between all those components of the nucleus is protons and neutrons, correct? So we have the nucleus. I mean, the beta radiation, it has no mass, but it has negative charge. So atomic mass is 0, atomic number is -1. Alpha radiation, atomic number is 2, atomic mass is 4. beta radiation, atomic mass 0, but atomic number or charge is -1. Okay, so alpha beta. Then we have something called, if I have alpha beta, then we have gamma radiation. So gamma radiation, and it has this one gamma here, has no mass, okay, has no atomic number either. So no atomic number and no atomic mass, 0, 0. And this is the symbol of it. So any questions so far? Any question? So we have other ones as well. So we'll go through the other ones. Any question about those major 3 ones? Alpha, beta, gamma. Then we will have our, if we have a beta here, the opposite will beta here will be here beta. The opposite will called positron. Positron. It has no mass and E, but the charge is positive. Okay, so positron is the opposite of this. This is negative. This is positive. Positive. Positron means positive. But those are positive positron, and this is beta is negative, the atomic number. Correct? So then if we have this, we have here called proton. The proton will be looking like this, H. Atomic mass is 1. Atomic number is 1. 1 and 1. Then the sixth one, all of them are 6. Then the last one is, of course, neutrons, correct? Neutron itself. It turns out neutrons, they have a mass, N. The mass is 1, but they have no charge, 0 charge. So atomic mass of neutron is 1, but the charge is, or call it atomic number is 0, atomic mass is 1. So those are the most famous 6 types of radiation. We have to memorize them, and if you take the next quiz and next exam, put them in a small tiny sheet so you can look at them and look at the whole thing. Now we'll do an example here. What will happen if an element will have some collision inside the nucleus, and then we'll get all this type of radiation coming out of this element. We'll take one big one, and then you can tell from the periodic table, anytime you have a radiation coming out, there is a possibility, not 100% all the time, but there is always possibility you'll obtain a new element. And that's what the industry is making, new elements from nuclear reaction, not chemical reaction. It's totally different. Chemical reaction has nothing to do with the nucleus. It has to do with the valence electrons out in the outermost orbital. But the nuclear chemistry has always to do with the nucleus itself. So let's look at an example here, and let's look at those 6 radiation coming off one of the elements that's used in the nuclear bombs to produce the nuclear electricity as well. So for peaceful and for military use. So uranium can be utilized in both ways, in the military as well as in generating electricity. So, and military means nuclear bomb, the same way like plutonium. So if you look at the uranium here, uranium, it has, if you look, check with me, I think atomic number, check, I'm not sure. Atomic number is 92. It has 2 isotopes. We'll take one isotope. Atomic mass is 235. And there is another isotope less abundant in nature, 238. So we'll take the most abundant one, which is atomic bomb, and electrical energy is utilized from this radiation giving off uranium here. We'll take 235. So atomic mass is 235, atomic number 92. The question is, I am getting out first alpha radiation 4 and 2. What will be the element coming here? I'm getting out beta radiation, which is 0 minus 1. What will be this element? I'm getting out a positron, positive, plus 1, plus an element. I'm getting, so alpha, beta, how about gamma? 0, 0, plus unknown element. So we have 4 now. 1, 2, 3, 4. We have neutrons, N with the top one, 0 mass, plus unknown element. And the last one here, we have proton, one atomic mass, atomic mass is 1, atomic number is 1, plus unknown element here. So somebody will help me to get the first one. So let's take the first one here out, and I want to see what will be the element here. Well, I put the element as X. Let's put the element as X. Now, this X here, the 4 here, with atomic mass, the sum of atomic mass. You see the arrow here? All those arrows here, separating the reactants from the products, correct? The same like a chemical reaction. In the left, your reactants, or reactant, in this case, one reactant, and you have products in the other side, in the right side. So in order to balance nuclear equations, atomic mass at the left has to equal atomic mass at the right. Atomic number at the left has equal atomic number, the sum, all atomic mass at the right. So what will be here? So what will be in the top here, guys? Somebody will tell me here, that will be what? 4 will be 2, correct? 3, correct? And 1. So the atomic mass of the new element is 231. And this is 92 minus 2 will be 90. So I go to periodic table and look at the 90, okay, look it up, and then I can see what is the element that has atomic number of 90. We're not look at this. This is not part of this. This is the only one. The atomic number, which is number of the protons, that will give us indication what the element is all about. What's the name of this element? Correct? 90. So somebody look it up for me. What's the element 90 is?
Thorium.
Thorium, TH?
Yes,
TH?
yes, TH.
Okay, TH. So let's take the X out now. Let's take the X out. And then, all right, TH. Okay? TH. With 200, so you can get the idea here. Thorium here, again, has 90 atomic number, 231 atomic mass, 231, I'm sorry. It's not writing very well. So 231. So how about the second one? Which one? The second one. What is the second one? Let's take it out here. Second one. Here it is. Second one. What will be atomic atomic mass, that's your X. Atomic mass, that's 0, correct? So will be what? 2, 3, 5, correct? If you add them up, it will give you the atomic mass at the left side. How about atomic number? How much? Atomic number? Come on, guys. 92 minus 1. 92 minus 1 will be 93. 93. Perfect. So what is the element at the periodic table that carries out value of the number of protons are 93? Which one? Which one, guys? 93?
Neptunium NP.
NT, capital N?
Capital N and P.
Okay, P. So 93. Let's take this one here. So this is 93. And the top is 2, 3, 5. Let me take this one out here. The X out. Oops, sorry. So that's the second one, correct? How about the third one? The third one will be? So the third one, what will be the third one? Plus, this is +1, correct? That's positron, +1. This is 92. So we take this one here out too. Will be what, guys? The mass, atomic mass is 0. So in the top will be still 2, 3, 5, correct? But this is 1, so it will be 90 what? At the bottom will be what? 91, correct? So 91 at the bottom. So, whoops, sorry. So here it is. Plus. Here it is. This is 235 in the top. And the bottom is 91. What that really is? Somebody will tell me? Somebody will tell me what the element 91 is? 91. What's that?
Protactinium PA.
PA?
Yes.
PA is Pennsylvanium, is it?
Protactinium.
PC or PA?
Yes, PA.
Okay, so I'll trust you. So you don't have the periodic table available to me. But anyway, so that's the whole thing. How about gamma now? I'll take all this stuff and then put the 3-1 gamma, neutron, and proton. Can I take the top ones? The one covered until now? Those 3? Take the other ones because it will be too crowded. Can I take them out? Take them out?
Yes, yes.
Okay, so let's take this out and we are looking for gamma, neutron, and hydrogen. Let's take those out here and then just put the new 3-1 so we can follow them much better. So it's too crowded because it will be too crowded. So now, how about neutrons? Has a mass of 1, but then the atomic number or charge is 0. Plus, what will be the atomic number? Atomic mass will be in the top. 2, 3, what? 4. If you add them up, it will be 2, 3, 5 at the left, correct? You have to add all the atomic masses at the left equal all the atomic masses at the right. Okay, guys? So then you have 92 here, correct? Can you see that? And this is 0, that's not charged, so that's 92. So the element is what? Still uranium. Because if you add 92 plus 0, it's 92. And that's uranium, correct? No change. No change. Now, how about the proton? Atomic mass 1, atomic number is 1, plus. Here is 1, so your element will be in the top 2, 3, 4, atomic mass. How about the 1 here? 91, correct? 91 minus 1 here will be 91. 91 is, you said what? The PA? It's a PA? What's 91 element?
Yes, PA.
Okay. So that's here. The only thing left is gamma. So that's 0 and 0. So we have the same element coming back again. 235 plus 0 is 235. That's uranium. 92, 0, 92. So the element is not affected by radiation of when it's radiating gamma. It's the same atomic mass and the same atomic number. So we have 6 radiation coming in. 6 radiation coming in. Any question, guys? Any question? Any question? So any question? Any question?
I actually don't know what to ask.
Okay. I'll give you we have to about 20 minutes or so. Let's do some questions here. You tell me what the elements will be, correct? So let's see what the element will be. We are after the elements, correct? We are after the elements. And as I said, we'll come Tuesday, we'll do so here it is. I have an element. What is the atomic mass of iron? Take any element you want, correct? So let's take iron. Atomic number of iron is what? 20 what? 26, correct? Check it out, correct? Atomic number is what? Atomic number is 26. Atomic mass is 50 what?
6.
Okay, now this is iron. What will happen if I lose gamma radiation of iron? What will be the element coming out? Tell me. I will give you a couple minutes to think about. What element will be? Come on, guys, don't let me down. You'll know it. What the element will be?
It's still iron.
It's still iron. Perfect. Why still iron? Because iron here, the 0 here, so then 26. 26 plus 0 is equal 26. Perfect. And this is 56. 56 plus 0 here equal the 56 here. So the element is iron itself, so no effect. So now let's see if we change this one here and say, let's take this iron here and let's assume iron is giving away a neutron, correct? So it gives away a neutron. Neutron atomic mass is 1, atomic number is 0. So what will be the element coming out? What the element will be coming out? Come on, guys, you know it. It's easy, not difficult. What will be? Remember that we can recognize the element by the atomic number, not atomic mass, by the atomic number. So what is the atomic number of an element coming off now, new one? What will be?
So 26 minus 0 equal 26. It's still
Still iron. Perfect. Perfect. That's another isotope of iron. So, however, the atomic mass will differ, correct? How much will be? How much?
56 minus 1 is 55.
Perfect. So that's another isotope of iron. You get the idea? You get the idea? Now let's assume that iron is now getting out alpha radiation. So we'll take out of this here. That's our assumption is this one here is taking out alpha radiation. And you tell me what will happen if iron is get alpha radiation out. Alpha radiation is helium atom with atomic mass 4, atomic number is 2. So what will be the element? The element has how much atomic number? How much atomic number? Come on, guys, don't let me down. You know it. How much?
24.
24. Perfect. Why is 24? Because you add those atomic numbers. 24 plus 2 makes what? 26. So how about the atomic? So first you can get the atomic the metal. So we'll make the atomic mass later on. What is the element in the periodic table that has atomic number of 24? What is that element? You go back 2, correct? That's 26. So 2 in the back to the left. What's the element? Come on, guys, you can see the periodic table.
Chromium.
Chromium, yes, Cr. Correct. Why chromium? Because it's the atomic out of iron we made chromium. Correct. How about the atomic mass of chromium now? 56 minus 4, because you have to minus this, will be 50 what? 52. Why 52? You can add those together as to equal this. Make sense, guys? Now let's take a beta out of this. Let's take beta out of this. So we take alpha. Alpha is helium, correct? Let's take beta out of this. And the beta has no mass, correct? Atomic mass is 0, but the atomic number is -1. So what will be the element here? What's the atomic mass of the new what the atomic number of the new element? So we can recognize that element by atomic number. Which one? Which one will be?
Minus 26 minus 1 is 27.
Yes, if you add those up, does it give you 26? Yes, it does. So in the top will be what? No change because that's 0. So in the top will be 56 as is. You add them up here, both will equal this one here, equal the number there. So what is the element with 27? What is the element with 27? That's come after the what? After the iron. So what's the element then? What's the element?
Cobalt, CO.
Cobalt, correct? CO. So cobalt has atomic numbers 27. That's very important to know the atomic number. That will give us the element. And atomic mass 56. You get the idea? Let's take now, we take alpha, beta. Let's take the positron. And let's take the positron. So let's take the positron. The positron has no charge, 0. However, it has +1. I mean, has no atomic mass, but it has a charge +1. So what's the new element will be? What will be the new element? Atomic mass of it? 25. 25 plus 1 makes 26. If you add those up together, makes the 26. What will be then the atomic mass? 56 and here 0 will be the same thing, 56, no change. What is the new element? What's the new element? With the 25?
Manganese.
Manganese, Mn. So you get the idea now? You get this idea? We'll have those further. We'll go further for this. We'll go further for this. So let's take now. Did we take gamma out? Yes, we do, correct? We did. Let's take gamma. So, and then the proton, I think. So let's take gamma. Gamma is 0 atomic mass, 0 atomic number. So the element will be what? The same as is 56 and 26. Add those up, give you this. Atomic number, atomic masses will be the same thing. Correct? So now we did protons. Did we do protons, positrons, neutrons, alpha, beta, and gamma? We did all of those. So let's take another example, another element. So pick up another element of your choice. Pick up any element of your choice and just let me know. Any question, guys? Any question to balance nuclear equations? Any question? Any question? Okay, so pick up any element and then we'll get all those 6 radiation out of it. So pick up any element. Come on, guys, pick up any element. Hello? Pick up any element, guys. Come on. Come on, guys, pick up any elements. Any element?
Iodine.
What's spell the what? Iodine. Okay, iodine. Okay, iodine. That's a good element. What's the atomic?
53.
53 atomic number. Atomic mass, how much?
127.
Okay. So now we'll have alpha, beta, gamma, protons, positrons, correct? Those 3 positrons and this alpha, beta, gamma, and neutron, sorry. So those 6. Okay, so this is positron. P plus here, positron. So now we'll get one at a time. First alpha. So you tell me the elements coming out. So this is alpha. Helium. Alpha is an helium atom, atomic mass of 4, atomic number is 2. So what is the new element? If there's a new element, you tell me the atomic number of it and the atomic mass. So as soon as you get the atomic number is, you will look at the periodic table. This atomic number corresponds to this element. So what will be the atomic number is here at the bottom? How much?
3 minus 2 is 51.
51, correct. And what will be the atomic mass of this?
127 minus 4 is 123.
Correct. What this element is, what's the name of this element with the atomic number? Always the atomic number will give us the element. Okay, what's the element?
Looking at the periodic table is antimony, Sb.
Sp, antimony. Okay, guys? Are you just looking at this? So that's the first one. This is the first one. So we took the alpha out. So we took alpha out. So alpha out. So this is the new element with alpha. Now we'll take beta. Beta, we said, has no mass. I mean, atomic mass is 0, but atomic number is -1. So what is the new element will be? What's the atomic number of the new element? Am I correct? Yes? 54, correct? If you add 54 minus 1, will be 53. What the atomic mass? So the atomic number is 54. Atomic mass is 127, no change. So what is the name of this new element with 54 atomic number? Always remember, that's the key here. This is the key to know the type of element you are dealing with coming out of this radiation. So what will be the element here, 54?
It's a xenon with like an X.
Xe.
Yeah.
Xe, xenon, correct? So we did now the beta out. So the beta, that's beta, atomic mass is 0, atomic number -1. So let's take gamma. We'll take gamma now. Everybody get the idea now? Everybody get the idea? We'll take maybe some worksheets in the coming Tuesday, 2 days from now. So gamma, atomic mass is 0, atomic number is 0. So what is the new element will be? What's the new element will be? Come on, guys. What's the new element? There is no new element. That will be 53. That will be 127. Why is that? Because if you add those to the zeros, you'll get the same value over there. If you add those to the zeros, you get the same value here. So gamma radiation is the only radiation that's give you the same element with no change in atomic mass or atomic number. Make sense, guys? Make sense? Okay, let's take now gamma is out. We'll take the protons. Okay, so let's take the protons. Protons is atomic mass 1, atomic number is 1. So what's the new element will be? What's the new element will be? Somebody will tell me? What will be new element? Come on, guys.
Is it tellurium?
Tellurium, Te?
Mm-hmm.
Well, it has to be 52 first at the bottom here, because if you add 52 to 1, will be what? 53. And in the top, how much will be? 126. Correct? If you add them up, will give you 127. And what is the element 52? You said tellurium?
Yeah, I did.
Te?
Yes.
Okay, so that's a proton. That's a proton. That's a proton. So let's take a positron and neutron. We have now this proton is out. Everybody get the idea? We'll have one worksheet extra when we come back 2 days from now. So now we are doing the positron. So let's do the positron. Positron is the same like beta, but no mass, 0 mass, atomic mass, but the charge is +1, positive, okay, positron. The beta is negative. Atomic mass is, atomic number is negative, -1. The positron atomic number is +1. So what will be the new element? So that's 0, so then the top will be 127, no change, correct? You add to the 0 will be give you in the left side. So how about the atomic number? What will be the atomic number? 50 what? How about 50 what? Come on, guys.
52.
52, correct. What's the 52? The 52 is what the element is?
Tellurium.
Tellurium, Te?
Yes.
Okay, guys. The last one here is neutron. The last one is neutron. Okay, so the last one is neutron. Believe it or not, that is the major thing of the whole chapter 3. So not ask you about details about things, something like this, but to ask you how to balance nuclear equation. And then we'll talk in the class about the application. The application is not really, we can talk about it now. So you can tell me what's the application of nuclear chemistry. Neutrons is atomic mass is 1, atomic number is 1. So what will be the atomic number of the coming element, the new element? What will be? What will be? Again, will be what?
52.
No. I'm wrong. That's a proton. Nobody even told me about this. Neutron has no charge. Come on, guys. Neutron has no charge, but it has a mass. So how much is this? Will be
53.
53, correct. And in the top, 126. So 53, that's iodine itself. That's another isotope of iodine. Yeah, a neutron does not have a charge. It's neutral, correct? But it has a mass of 1. So that will conclude all the balancing chemical equation. When we come back Tuesday, we'll have another worksheets. Now, we'll talk about just for a couple, 3 minutes left about the application for nuclear chemistry. Somebody will tell me what's the most important thing about nuclear chemistry applications. You know, we talked about the extreme case, which is in the military, you can produce nuclear bombs out of them. But there is a positive thing about this. It's used in the health related situations. A small tiny dosage of those radiation can kill tumors. And they are used now widely in when you hear something about cancer treatment with radiation. So think about those radiation, alpha, beta, gamma, even gamma. Gamma is used, it's highly energetic, the highest one, gamma radiation. So a small, tiny dosage, not too much. If you use too much of gamma radiation, you will be barbecuing the patient, him or herself. So will be barbecued because they are highly energetic, especially especially gamma. So, but small dosage are really pinpoint to where the tumors are, and then you take them one by one by this radiation. So widely it's used in the medicine area. So in the medicine area, so that's to fight tumors, to fight all types of cancers, but not in such very sensitive area. You can use those radiation on the brain. It's too risky. But in some other areas of tumors, skin, whatever, muscle tumors, whatever is stomach tumors, so you can use those type of radiation, especially gamma. Gamma is highly used, and the idea, all those radiations are particles except gamma, believe it or not. Particles, they really they carry some sort of mass, correct? But not the mass in the sense like beta almost atomic mass is 0, atomic charge -1. But those are particles except gamma. Gamma is a wave, can go through the objects. So if you have a gamma, can go through a wall. But all the other ones, they can be absorbed in the wall itself, or they can bounce back to the source. So, and that's the most application ones for the nuclear chemistry. Nuclear chemistry is used for military part of, products, or for health. Health related is mainly for cancer treatments. So they are treating cancer with the radiation, especially gamma radiation. So 9:15, time is up. I will see you in Tuesday, 8:30 in the morning. Thank you very much. You have any question? I'm open. Any question, guys? Any question? Any question, guys?
No.
Okay, I'll see you then.
No questions.
I'll see you then Tuesday at 30. So I was at the conference, so it was very nice conference we have attended. Okay, guys, see you then, okay? I'll stop sharing now. Thank you very much.